When we looked at the Romberg method in the last video, one of the key things that was essential to know was the order of the error terms, and once you'd remove the leading order error term, what the next order error term was. We're going to look at a method today that allows you to do something a little bit similar to the Romberg method when you don't know what the order of the error is. Okay, so this method is applicable when we don't know how the error changes with the step size. For example, if we have a complex functions that are output of computational models, we have no idea what the truncation error might be. For example, rainfall prediction from a weather model. To illustrate the method, what we're going to do is we're going to form a series of approximations to our integral using, again, the trapezoidal method. And just for ease, we're going to take step sizes of h on 2, h on 4, h on 8, etc. So we're still going to use the trapezoidal rule to illustrate this, but it's applicable for any kind of integration technique that you want to use. What we can now do is we can plot these integral estimates here as a function of our step size. And what we hope to do, as the step size gets smaller and smaller and smaller, we would expect that our actual integral becomes closer and closer to the exact integral. Okay, so if we can take this series of estimates and extrapolate to h is equal to 0, then perhaps we've got a good estimate of what the actual integral is. So what we're going to do is we extrapolate using polynomial extrapolation. Effectively that's polynomial interpolation, but we're going outside the region that we know, and we're going to extrapolate to a step size of h is equal to 0. So let's just have a bit of a look at this. So we're going to use the graphical Romberg method, that's what this method is called, and have a look at this integral here. So it's just the integral of cos from 0 to pi on 2, and whoops, sorry about that. And if we actually tabulate the trapezoidal rule estimates for different step sizes, so if we take one interval, the step size is pi on 2, and we fit a triangle to this point here. If n is equal to 2, we know that the step size is pi on 4, so we've got 2 trapezoids, so we obviously get a better estimate, and we can see that very rapidly, as we go up to more and more intervals, and we're doubling it each time, our trapezoidal rule estimate is getting better and better, which is of course what we would expect. The analytic solution here, of course, is that this integral is equal to 1, and we're actually doing pretty well down here. Regardless, let's have a look at the process. So let's plot the answers. So let's take the first 2 points, that is n is equal to 1 and n is equal to 2, and these are the two estimates of our integral, 0.785 and 0.948, and this is pi on 2 across here, that's pi on 4 there, and we can see that we have our two estimates. If we now fit a polynomial, we can only fit a linear polynomial. We fit a polynomial to those two lines and we extrapolate to h is equal to 0. We get an estimate for the integral that's about approximately 1.1, I don't know, 05, something like that. Let's use the first 3 points. So these are the pi on 2, pi on 4, pi on 8. Let's fit a quadratic to those 3 points and then extrapolate to h is equal to 0. That's that point there. And we end up with something that looks pretty close to 1 actually. It's a little bit different, but we can then use the first 4 points, fit a cubic, extrapolate to 0, first 5 points, etc. So it's not obvious here exactly what's going on here. I mean, obviously the error is going to 1, but let's just plot it a little bit differently. If we plot this axis here in log coordinates, and obviously we can't go down to h is equal to 0 in log coordinates because that's often at negative infinity, but let's just go to a very small number. We can see that the error is very rapidly decreasing and we're very, very rapidly going to a uniform value. So, to summarize, if we know the form of the error, we can always use Richardson extrapolation. And the way in which we do that is to combine the errors at different step sizes to remove error terms. which gives us a more accurate answer, and we can use this technique recursively to remove higher order error terms. The recursive way of doing things is known as Romberg integration. If, however, the form of the error is unknown, we can use the graphical Romberg method, which uses a sequence of smaller and smaller steps, and then we extrapolate from those to h is equal to 0.